too. I mean, it's fine with me.
Well, for me it wasn't that bad, but that's just me.
Okay.
Everybody else.
Yeah, this microphone, is a good quality one. It will pick up everything. But as far as the class is concerned, I think you guys just want to hear my voice clearly. So if the other one, is that okay? I mean, is the other one fine, in terms of voice quality? You can still kind of hear what I'm saying?
I don't know.
I can try that next time, and you guys can compare and tell me which one you want. Okay, because I have both, so I can choose which one, whichever one works best for the class, I can just use that. Any other questions about the Fibonacci trace or the homework assignment that is due next Wednesday? No questions? Okay. If there are no questions, we'll continue and combine return values with more stuff that we have done so far. Okay. In other words, instead of beginning a new topic, which I could do also, we'll just kind of go back to stuff that we already understand, and then we'll basically say, okay, is there a different way to specify the solution, the algorithm, but this time using return values and possibly recursion? Okay. The first one we'll kind of go back and re-explain, or at least have a new way of looking at it, is binary search. You look at binary search and go like, well, but we have talked about that quite a few times already. What else is there to talk about with binary search? Let's see if we can define binary search this way. Okay, so this binary search, it will require a number of parameters. In other words, tracing this one is going to be a little bit difficult because we have to set up a lot of parameters. We'll pass by reference A, which is an array. We'll pass by value a whole bunch of stuff, because you need to specify where is the beginning of the array that may contain the value k, where is the end of the array that may contain the value k, what is the value k. Okay, so A, B, E, K are all parameters that you have to pass to the binary search algorithm. Inside the algorithm, we have a local variable m to do exactly what m used to do in the conventional algorithm. Which means the first thing we want to do is to compute the value of m. Well, we don't actually have to do that. So we'll go ahead and change the logic a little bit. But there are options, okay? We used to check b is greater than e as the exit condition of the repeat until loop, right? Because when b is greater than e, that means no part of the array can possibly have the value k anymore, and as a result, we can get out of the loop and conclude and say, okay, the value k is not in the array anywhere. But in this case, using recursion, I'm going to use a conditional statement to do it. And I will return the value of false when b is greater than e. Okay, so you have to, okay, let me finish the algorithm first, and then we'll kind of come back and take a step back and look at the algorithm or the subroutine from the perspective of the caller or the invoking code. Okay, if b is greater than e is false, then we will go ahead and do something else. Okay, so I'll specify an else here, because one thing I have to do, regardless of the condition after this, is I have to compute m. I have to find out what is the index of the middle element within the array that can still contain the value k. This part is exactly the same as before. It's b plus e, the whole thing divided by 2, and then we take the floor of that. Do you guys still kind of vaguely remember that? Okay, very good. And then we still have to check certain things. We still have to check to see if a bracket m is less than k. If that is true, we do one thing. And then we have to check if it is the other one. If a bracket m is greater than k, or better yet, we specify k is less than a bracket m, then we do something else. If that is also not true, we will do yet something else. And if, and define sub. If anyone wants the challenge, we can basically look at this as a challenge. In other words, we'll try to follow this algorithm without indentation. I think that's a pretty good challenge, okay? Because we have a conditional statement inside the conditional statement, and the whole thing is inside the definition of a subroutine. So that means, when I'm done here, okay, let's say I execute this statement on line 14, where do I go next? Which end if am I talking about? Well, in this case, because the end ifs are right next to each other, I actually go all the way out to line 19. So it's actually not too bad in this case, but nonetheless, the indentation is actually going to make a major difference. Okay, the array is still going to be sorted in a non-decreasing way. If the array is sorted in a non-decreasing way, and k is already larger than a bracket m, which one do I update? Do I update b, which controls the beginning of the portion of the array that may still contain the value k, or do I control e, which controls the end of the range of the array that may still have the value k? We update b, right? So in the good old way of doing things, which we are not going to do anymore, we update b to become m plus 1. It is not m, but it is m plus 1 because a bracket m itself is also not matching the value k, and therefore you have to add 1 to it so that we start with the next element on the right-hand side. But this is the old way of doing things. With recursion, this is what we do. We say return, and then this time we return the result of invoking binary search again, and we pass a to a. We pass, okay, we'll specify something here later. We pass e to e, and then we pass k to k. The only one that we are not passing the same way as before is b, because the way we specify the parameter b for this new invocation is m plus 1 is now passed to the parameter b. Okay? In other words, we are turning an iterative algorithm that uses a loop into a recursive algorithm that only has conditional statement and recursion but no loops anymore. In the other case, we have to update e, which means I can now return, invoke binary search, a still goes to a. In this case, b goes to b because we are not changing the beginning of the range of the array, but we are changing the end so that it becomes m minus 1. And then we are not changing the value that we are looking for, so k still goes to k. Let me just change the indentation because it's starting to bother me. Has the indentation or the lack of indentation been bothering you with this algorithm?
Yes.
That's good. That's the whole point. That's the whole point of fixing it only now and instead of earlier. Okay. Much better with all the indentations in place. Don't you think this looks a lot better? Okay. In this case, what do I return? Okay. Let me just get rid of this portion here and think about it. I can only get to here because of what? I can only get to here when b is less than or equal to e first, right? Because if b is greater than e, I would have returned false right away, right? So because I'm in the else portion of the outer conditional statement, it means that, some portion of the array may still contain the value k. Great. Then I go ahead and compute the index of the middle element, which is m, just like before. Then I perform, some comparisons. I check whether a bracket m is less than k. No. I check whether k is less than a bracket m. No. Then I can get here. So what do I know about a bracket m and k at this point of line 16 of the pseudocode? They have to be the same. So that means I don't really have to say else if k equals a bracket m because I already know that a bracket m does equal to k at this point. Is it wrong for me to specify else if k equals to a bracket m then? It is not wrong. It does not change the program's behavior at all. It's just redundant, and it is basically a waste of execution time. Does everybody get that part? Okay. So in this case, I just return true because the algorithm or the subroutine is supposed to return true if k is found anywhere in the array. Is that okay so far? Once we confirm that one of the elements has the value k, we just say, woohoo, we found it, return true. But if we can also confirm that nowhere in the array can contain the value k, we have to return false, so that the invoking subroutine knows that that portion of the array does not contain the value k. Are we doing okay so far with the overall logic? Yep.
How does the beginning and the ending change? You're only modifying the m plus 1 to m minus 1. How is the beginning number subscript will be different? How is that going to be different? How is the ending going to be different every time it goes through this loop?
Because each time I invoke binary search, each invocation has its own B and its own E.
Okay.
I change B and E when I invoke the next invocation. I don't change the variable B, I don't change the variable E, but when I pass the parameters to B and E, that's when I make the change. Okay? Let's go ahead and trace this algorithm for a very, very simple case, like an array of 3 elements, okay? Because that's basically all we need to see how this works. Okay? But this algorithm, we have to start with some global, it doesn't have to be global, it can be local too. Well, I might as well do it over here too. So I can define another subroutine called main. And this time I have A as an array, which is a local array. Okay? But in this case, I have to be a little bit more specific and say A is an array of 3 elements. This is pseudocode. I can spell this out as in as many words as I want, which is nice. And inside here, I can do the initialization by hand. I can say A bracket 0 gets a value of 4. A bracket 1 gets a value of 7. And A bracket 2 gets a value of 11. Okay, doesn't matter what it is. And then I will invoke the subroutine. In fact, I will print the result of invoking the subroutine just like with my other subroutines or other examples. So in this case, I will invoke binary search, and I will pass my local variable A to parameter A. Now how we represent this, because now parameter A becomes a reference to not a single column, but a range of columns. Okay, so we'll talk about this, how we can represent that. And then we have to specify B, and B has to be 0 to begin with, just like in the iterative version of the algorithm, because before the first comparison, we have to consider the entire array as being possible. The k it can be anywhere within the array, so 0 is the index of the first element that can have the value k. Likewise, bar A bar minus 1 is the index of the last element that can have the value k, and we'll go ahead and look for a value that is not in the array. Let's look for 5. So 5 will specify k when we invoke the subroutine. And define sub, and outside of the subroutine definitions, we just invoke main, which is the C way of doing things. Okay. So once again, this entire program does not use a single global variable. Are you guys starting to see, how the parameters combined with a return value means that we don't need global variables at all? Okay, which is nice. Okay, this is what we want it to be. And now we can give it line numbers, and then we'll trace it. This one is going to be a little bit long and tedious to trace, but nonetheless, it is a very good example to illustrate what we can do with subroutines, return values, and passing parameters of different sorts. Here's my algorithm, and I will trace it with the next window. This is going to